Hello, and welcome to my video series of algorithms. This is part 4 of Module 4, focused on greedy algorithms. In this video, we will discuss the minimum spanning tree problem. Imagine that you are running a secret agent organization and need to send a classified message to all agents. Some agents can contact with each other, while others cannot. Of course, the risk associated with each pair of agents communicating varies. Your task is to determine which pairs of agents should make contact to ensure that the message is sent to all agents while minimizing the overall risk. We can represent this scenario as a graph. Here, the agents are represented by the nodes. If a pair of agents can contact each other, we add an edge between them. The edge weights indicate the risk associated with making contact. The higher the weight, the greater the risk. The red edges in the graph illustrate the solution with the lowest total risk. That is, the sum of the red edge weights is the minimum among all other solutions that can connect all nodes. Because all nodes are connected, we know that all agents have received the message. The problem can be formulated as the minimum spanning tree problem, or MST for short. Specifically, we are given a connected, undirected graph G with its node set V, edge set E, and edge weight set W, which contains no negative edges. The goal is to find a subset of edges T with the minimum total weight while keeping all nodes connected. Here, we say T is minimum because it has the minimum total weight. And we call it a spanning tree because it connects all nodes in the graph. Note that we do not allow negative edges because it does not make sense to have negative risk, where secret agents meet with each other to reduce the risk of being exposed. Despite the problem being defined as finding a subset of edges, it implies finding a tree. If T is the minimum subset of edges, it must form a tree. Otherwise, it would have the same weight as the minimum tree. To prove this, consider that if T is minimum but not a tree, it must contain a cycle. By definition, breaking the cycle by removing some edges will not disconnect the graph. Since there's no negative edge, removing edges will not increase the weight of T. Therefore, we can keep breaking cycles contained in T until it becomes a tree. Since T is minimum, removing edges cannot decrease its weight either. In this case, we have proven that T is either a tree or has the same weight as the minimum tree. We can solve the MST problem using greedy algorithms. Recall the shortest path problem discussed earlier. While the shortest path problem constructs paths, and the MST problem constructs a tree, both aim to reach all nodes in the graph with the minimum total weight. In this case, we can borrow the intuition for solving the shortest path problem here. That said, we propose 3 greedy algorithms. First, we can progressively grow the tree by adding the cheapest edge that connects a new node. This idea is called Prim's algorithm. Second, we can continuously add the cheapest edge if it does not create any cycle. This idea is called Kruskal's algorithm. Third, starting with the full graph, we iteratively remove the heaviest edge if it does not disconnect the graph. This idea is called the reverse delete algorithm. First, let's discuss Prim's algorithm, which continuously reach new nodes with the cheapest cost. The setup of the algorithm is very similar to Dijkstra's algorithm, which was discussed in part 2 of this module. To begin, we will select an arbitrary node, say agent D, as the starting point. We also need to maintain two sets, the visited set and the unvisited set. The visited set is initialized with the starting point D, and the unvisited set should contain the rest of the nodes. We record the two sets at the top right corner of the slide. Here, from nodes in the visited set, for example D, we have two ways to visit a new node. We can either visit B with a cost of 56 or visit C with a cost of 37. Both edges are highlighted in green. According to the greedy principle, we will visit C with the lowest cost edge, CD. Now, we include edge CD as a part of the spanning tree T. We will also include node C in the visited set. We then iteratively repeat this process. With nodes in the visited set, for example C and D, we can now reach A, B, and E using the corresponding green edges. Note that Prim's algorithm differs from Dijkstra's algorithm in that it does not need to add the accumulated path cost. For example, we can reach node B from C with a cost of 13, which does not include the cost of visiting C from the starting point D, 37. This is because Prim's algorithm is not trying to construct a path. Instead, it just tries to recruit a set of edges. That said, the edge between B and C has the minimum weight, and since B is unvisited, we will choose it to visit B. Similarly, we will recruit the edge BC into the spanning tree. We will also include B into the visited set. Next, among the green edges that can visit new nodes, the cheapest edge is AB. Since node A is unvisited, we will choose it to visit A. Now, we include A into the visited set. The next cheapest edge is BD. However, since both B and D are already visited, we will not include this edge. The next cheapest edge is CE. Since E is not visited, we will choose this edge. Similarly, we can include E into the visited set. Since all nodes have been visited, we can terminate the algorithm now. Here is the pseudocode for Prim's algorithm. You can compare it with Dijkstra's algorithm and find their similarities. Before discussing the next two algorithms, we will first sort the edges by their weights. The second algorithm is Kruskal's algorithm, which iteratively selects the cheapest edge if it does not create any cycle. To begin with, we define sets to indicate whether the nodes are connected by the recruited edges. If two nodes are connected by the recruited edges, we put them in the same set. At the beginning, no edge has been recruited. So, all nodes are disconnected, and they are put individually into disjoint sets, as indicated by the square brackets. We can use the sets to easily detect cycles. Specifically, adding an edge to connect two nodes in the same set will create a cycle, because the nodes are already connected before adding that edge. On the other hand, adding an edge to connect nodes from different sets is okay. But we need to merge the corresponding sets to indicate that these nodes are now connected. From the sorted edges, we see that the cheapest edge is AB. Since A and B are in different sets, we can take the edge. Correspondingly, we will merge the sets that contain A and B, respectively. The next cheapest edge is BC. And since B and C are in different sets, we can take this edge. Similarly, we merge the sets for B and C. The next edge is CD, which again connects nodes from different sets. And we shall take this edge as well. We merge the sets for C and D. Now, for the next edge, BD, we see that the nodes B and D are in the same set, which means taking the edge will create a cycle. In this case, we will not include BD. We mark BD for deletion. Next, for the edge CE, it connects nodes C and E that are in different sets. We can therefore select this edge. We merge the sets for C and E. The final edge is AC, which connects nodes that are already in the same set. Therefore, we will not include it. At this point, we have considered all edges and can terminate the algorithm. This is the pseudocode for Kruskal's algorithm. The last algorithm is called the reverse delete algorithm, which iteratively deletes the heaviest edge from the full graph if it does not disconnect the graph. We begin with checking the last edge, AC. Removing it will not disconnect the nodes A and C, because they can still be connected with the path A, B, C. As a result, we can delete it from the graph. The next heaviest edge is CE. We cannot remove it since that would disconnect E. The next edge is BD. Since B and D are also connected by the path BCD, we can remove this edge. Next, we cannot remove the edge CD since it will disconnect C and D. Similarly, we cannot remove the edge BC. And finally, we also need to keep the edge AB. As we have considered all edges, we can terminate the algorithm at this point. Here is the pseudocode for the reverse delete algorithm. Besides the above three algorithms, there is another algorithm called the Barufka's algorithm for solving the MST problem. It can be considered as a parallelized version of Kruskal's algorithm, where multiple light edges are recruited at the same time. You can find more information online if interested. In summary, we have discussed the minimum spanning tree problem in this video. We have presented three algorithms for solving the MST problem. They are Prim's algorithm, Kruskal's algorithm, and the reverse delete algorithm. In the next video, we will talk about the implementation details and analyze their time and space complexity. Thank you for watching, and see you next time.